Hello everyone, welcome to this webinar. My name is Michel Ram and I am a scientific developer here at Scientific Volume Imaging, or SVI for short. Today we will discuss the Array Detector deconvolution option available in the Huygens software. If at any point you have questions during this webinar, you can send them via email to info@svi.nl. With that said, let's get started with the webinar. In confocal point scanning microscopy, the microscope example is excited point by point, and the emitted light of each of these points is then captured with a photodetector. This information is then converted to an electrical signal, which is saved as an intensity value for each pixel inside your image. During acquisition of regular confocal microscopy, a pinhole is positioned in the optical path to block the out-of-focus light. Its size is often chosen so that the first airy disk of your emitted light is captured. By closing down this pinhole, you can improve the contrast in your images. However, at some point, you really start to lose important signal and your images will become very noisy. A confocal setup, although suitable for many applications, effectively discards information at two stages. First, the pinhole rejects useful signal from the emission point, and second, the detector also ignores the spatial distribution of the emitted light. The array detector acquisition works a bit differently by actually measuring this distribution of light. And by capturing this distribution on not one, but multiple spaced out detectors, you are left with more spatial information from the emitted light, which can get even better results from deconvolution when using the spatial information of all detectors. Because you are saving a complete image per detector, this does mean that you are working with more data per image for unprocessed array detector images. And to perform analysis, it is useful to reduce the information to a single super resolution image. Now, how does one go from multiple images from different viewpoints to the same object to a super resolution image? Well, the detectors are often aligned to collectively obtain the light from this first airy disk. And each of these separate detectors then acts as a smaller pinhole, collecting only a fragment of this disk, which means they independently have a sharper image, but with less signal than a regular confocal microscope image would have with one airy disk. The differences in these positions of each detector also means that the images will appear shifted with respect to each other. However, by then shifting back these separate detector images to overlap the image from the central detector and adding them to each other, this will result in an image with an even higher resolution and more contrast. And by using deconvolution, we can get even better results of up to 70 or 90 nanometer resolution. This does, however, require a priori knowledge of the relative positions of these detectors, and any deviation from these positions due to misalignment of the optics can really impact your image quality when doing this acquisition. Array detector microscopy can be performed with commercially available array detector microscopes. But we also support other commonly chosen layouts and even allow for custom ones. So if you're interested in doing Huygens deconvolution with a custom array detector microscope, feel free to contact us. If you have a custom setup, for example, that acquires 23 detector images in a nanospat array configuration, you can use the file series tool to open them as a single Huygens array detector image, and after validating the microscopic parameters and correctly setting the detector spacing in the array detector parameters window, you can use Huygens' array detector deconvolution options even for your images. Now let's jump back in time a little bit. The first array detector deconvolution option in Huygens was added back in 2018 with version 18.10. This included support for the ArrayScan's first generation machine, with support for the virtual pinhole mode, as an addition to the confocal option, but this also introduced the addition of our Array Detector CMLE deconvolution mode, using the spatial information of all 32 detectors in super resolution mode, and even ArrayScan's fast mode with its faster acquisition of 4 pixels simultaneously. And later, with the arrival of the ArrayScan 2, a new way to save these large files was introduced. This was done by saving the images in Shepard summed rings. Here, the individual detectors are already shifted back to align with the central detector, and they are summed per ring. This leaves you with 4 separate detector images. However, this does not provide the best results with deconvolution, as some of the positional information of the multiple fields of view is already combined per ring of detectors. It is still possible to get the raw 32 detector data in ArrayScan 2 systems. Please contact Zeiss for more information. And all the methods that I mentioned before also include, of course, the multi-photon excitation deconvolution. And even to get even more out of your imaging setup, we also included the possibility of distilling an experimental PSF, including the Shepard Array Ring 2 images. By using the Huygens PSF distiller from version 2104 and up, you can distill PSFs from bead images and deconvolve them with a measured experimental point spread function. Here we see an ArrayScan 2 Shepard 4-ring image provided to us by Gabriel Krenz and Doreen Milius from the Imaging and Optics facility within the Institute of Science and Technology in Austria. This beautiful zoomed part of the image of murine kidney samples really shows the improvement in contrast you can get from deconvolution. Here you can see both the XY view and the XZ representations below, before and after deconvolution. And in order to obtain such nice images, we visualize which of the images is most suitable for deconvolution when opening CZI files that contain more than one image. The colors are used to indicate raw usable data for deconvolution with the green color. Partially pre-processed data is shown in orange, and it can still be used for deconvolution. But if the data is not suited for true deconvolution, it is shown in red due to the data already being processed. After opening the image in Huygens, you can view the dimensions in the Statistics tab. This will show you the number of detectors for this opened image. In this case, here we see the ArrayScan 1 fast mode. This is the image with 16 detectors. And note that the pixels are elongated in Y by 4 times. This is because in the raw data, the vertical information is mainly stored in the vertical 4 central detectors. After processing and or deconvolution, this data can be shown back into square pixels. For the ArrayScan 2 with Shepard rings, we denote this as orange as the rings have already undergone a step of processing by shifting back the images and then summing per ring. And finally, for the ArrayScan 2's multiplex mode, the data is already too processed in a way that we cannot do meaningful deconvolution with it. CZI files contain a lot of metadata, and the microscopy type and even the array detector acquisition mode is automatically read from these images and set by Huygens. Information such as the detector spacing or any rotation in the alignment or aspect ratios in the detector grid is stored in the array detector parameters on the bottom left. And soon, for even more quality control, the positional information of the raw detectors can be inspected by viewing these detector positions as measured from the image content. This will come later. Huygens deconvolution of array detector can be performed with a theoretical PSF and a measured PSF. And then there is still the option of performing deconvolution by combining the PSF information of all 32 detectors into a single image beforehand, or by deconvolving each detector image separately with their own PSF. It's also possible to deconvolve your images into a super sampled pixel grid by selecting Super XY. Here we increase the number of pixels in X and Y by a factor of 2 to obtain even higher resolution. This does cost more system memory and takes a little more time than the previously mentioned methods. But after selecting your method of choice, this is all handled automatically within the pipeline of the Deconvolution Express or the Deconvolution Wizard, so no manual pre-processing needs to take place. And all of these methods heavily benefit from GPU acceleration. Here we see an example of an array detector deconvolution image using the 32 detectors of an ArrayScan microscope, an ArrayScan 1 microscope. So on the top left we see a confocal equivalent obtained by summing the raw detector images, and on the bottom right we see the result after deconvolution with Super XY. From this image we can obtain at least a 90 nanometer 2-point resolution on single channel images. However, using a Super XY array detector deconvolution on multi-channel images of GataQuant nanorulers, we were able to separate differently stained objects that are spaced 70 nanometers apart. Here we see a zoomed in region of an ArrayScan fast image. Note the elongated pixels in one of the separate raw detector images. As I mentioned, this is because the information of the pixels is mostly captured in the central vertical line of 4 detectors during acquisition. After processing or combining the information of all 16 detectors with deconvolution and their relative shifts into a single image, we can retrieve the square pixel grid. This is done by using Super Y deconvolution, and as you can see from this example, we see a great improvement in contrast. Note that also the sampling rate is restored to the expected square pixel grid after processing. The next video contains a beautiful SFP rendering of neurons that were acquired in the fast mode of the ArrayScan and later deconvolved with Super Y deconvolution. You can really see much more clearly and with great detail what these objects look like. During imaging, there is often the optimization problem, where you must consider multiple aspects. Ideally, you want great resolution and high signal-to-noise ratio, but that often goes at the cost of imaging speed, or even at the cost of photo bleaching your samples. With deconvolution, the range of these aspects are effectively widened, and this way you can either improve the signal-to-noise or acquire a little bit with with smaller samples or higher sample sizes in order to, after deconvolution, improve the signal. It is important to note that Huygens deals with PSFs that are normalized. So the sum of a signal for a PSF is 1. This means that we conserve the energy. As mentioned before, you can use the Huygens CMLE algorithm with either a theoretical PSF or a measured PSF. And the Huygens PSF distiller works by measuring spherical bead images and then generating a PSF from that for all detectors using the information from these imaged beads. After deconvolution, you of course want to perform analysis. And Huygens is known for its maximum likelihood-based deconvolution algorithm. Combined with the fact that we generate a PSF specific for your image based on its microscopic parameters, and using the detector info position of the array of detectors, you can get great results. There is also the option for using beads to distill an experimental PSF, as I mentioned, which can then be used to deconvolve your images or keep track of your microscope quality as a quality control. For images with refractive index mismatching, a theoretical PSF generator keeps in mind the spherical aberration and even corrects for it during deconvolution. Within Huygens, efficient brickwise processing and multi-threaded workloads for CPUs with high core counts, and even with the help of NVIDIA's multi-GPU resolution, this means that the processing can be done even faster. We also provide extra image restoration algorithms such as stabilization in both Z or time and chromatic aberration correction for multi-channel images. And when using Huygens, you can do reliable image analysis and quantification after restoration because the energy is conserved. So it is important to note that the Huygens deals with normalized PSFs. So the sum of the signal for your PSF is 1. And this means that we conserve the energy. As mentioned, after deconvolution, you want to do analysis. But before you get to that, make sure to check your images of both before you have done your array scan or array detector processing and after. We have seen data from other customers that was processed by other software where the sum in total intensities was orders of magnitudes different from the raw data. This strongly indicates that the energy is not properly conserved. And to check this, you simply open the image in the Huygens main window, and besides the histogram tab on the top right, there is a statistics tab. Here you see information about the size of your image, but also the statistics per channel. And this shows the information on the image's minimum and maximum intensity values and their respective locations, but more importantly, it also shows you the sum value of all pixels in your image. And this should be relatively the same before and after deconvolution. Here you can see it for a multi-channel image, where the sum value is shown per channel. It can vary by a slight factor due to Huygens' correction for background values, or PSFs of objects around the edges of the image can influence this. Bleaching correction for time series will also influence the total signal, and even crosstalk correction has an effect. But it should never be that the total summed signal differs by orders of magnitude after deconvolution. So be mindful of this and really verify this is not the case before you do analysis, as this can really impact your measurements. A good idea also is to check your images from the side views in XZ and YZ using the twin slicer or another tool of your choosing. Here you can also compare regions of low signal to check for signs of over-restoration after deconvolution. You can also compare the image data for multiple acquisitions or check the many deconvolution options that we have by working with the batch processor within Huygens. You can create templates and use those in a deconvolution workflow to automate deconvolution for you. Once you're happy with the results, you can save it, the template, and then use that workflow in batch on the rest of your data. If you are interested in trying out Array Detector deconvolution in the Huygens software, please don't hesitate to contact us or fill in the license request form on our website. And if you have any remaining questions, please send them to us via info@svi.nl and we will get back to you within 24 hours. This was the webinar on Array Detector deconvolution, and I wish you a good rest of your day.